Hello everyone, welcome to Turing Complete episode 3. Today I'm first going to start off by explaining some stuff I've done in the meantime, in between episodes. And after that I'm going to do some more explaining, because we're doing math today.
Oh, hello. Bye-bye.
There we go. Right, okay, so first off I want to go over two things. I have improved the double trouble circuit, this mess, where at least two inputs had to be on for the output to be off. On. My bad. Right? So here, what happens is, first of all, the obvious is that if you flick a lever, a piston extends, putting the composter upward, right?
But
that makes sense.
Function?
So, each composter, I'll quickly explain. A composter, right? If you come over here.
Yeah.
Right? If I quickly grab a comparator and redstone dust. So you can see the 0, 0, right? That's because the composter's empty. Ignoring that you're in it.
Yeah.
Then if I put seeds in it and fill it up by one level, it goes up to 1. And then if I were to fill it up again, then it's 2, and then 3, 4, 5, 6. Come on. 7. And then it's done. So this is a thing that allows you to basically encode in octal.
Yeah, from
right?
0 to... Yeah.
Yeah, 0 to 7.
Yeah.
That's octal.
No,
Which
8
is...
is one thing, right?
Sorry?
I saw the number 8 appear as well.
Oh, really?
4, 5, 6, 7. One more.
Oh,
8.
yeah. Okay. Anyway, that's not important. The important part is that if you fill it up by 1, then it's 1. Right?
Yeah.
So that's exactly what I've done here. Each of these composters is filled up by exactly 1 level. So that if it gets pushed up, the comparator behind will notice 1. Right?
Yeah.
Then, what happens is these comparators in this direction will then take the behind out input, so this torch for this one, the torch, minus, because it's in subtract mode because of this extra red little torch at the end.
Minus
1, which, if you look, now it's 15, because that's what the torch outputs, because it's 15 minus 0. Then if you flick this if you flick the lever, now it becomes 14. And these ones are all still behind output minus 0, so it just outputs 14. Then, what happens here is you have another torch saying 15, and then you subtract what is incoming from this 15. So this one is technically not necessary. This would also work, but as you can see, it forks off to this one. So instead, you just put a
Yeah,
comparator.
and then this
And then
outputs 1, and
1.
you need, in the end, you need 2.
Exactly. And so this piece of redstone dust will output exactly how many inputs you have. So as you can see, if I flick 3, then it becomes 3.
Yep.
And if I flick all 4, then it's a 4.
This is an even more advanced version of double trouble, since this keeps track of the amount of inputs.
Exactly. And so in this case, for double trouble, you just make sure that the redstone dust is too long before you repeat it and then send it to an output.
So with the comparators, you can basically do math with logic gates.
Absolutely. So I quickly want to make sure that I, give credit where credit is due. So I'm quickly going to look up where I found this, and I will link it in the description down below. So this part, this whole thing with the compost, by the way, very nice about this system is you can also put the inputs literally right next to each other. It does not have to be one block apart, as I did over there. Anyway, this was found, or at least I found this from Xane, I don't know, Zane256 on Reddit. I will link it down below, so you can see the machine in action there as well.
You still need one spacing between every one.
No. Because technically, what you can do is this.
Or remove this line. Yeah.
And then now they're fully independent if you were to place them next to each other. Just for the sake of simplicity, I spaced them out for this one. But for the next one, over here, I found a better solution for this monstrosity that we built last episode, which was that it counts the number of inputs and outputs the proper binary signal. So as you can see here, I put all the inputs right next to each other. And it works the same way, except now instead of over there, I put redstone in between each of these comparators so that you can like actually see what the redstone was doing. Now it doesn't do that. And it's technically the same circuit. Now 0 inputs are on. And now see 1 input is on.
1, yep.
Right? And then 2, and then 3, and then 4. Right?
Yep.
Makes sense. All right. Then the next part is again something I found on Reddit. This was found by Am1 Reto, I guess, is what I found on r/redstone. I'll link it down below again. And that is this part of the circuit, which basically takes the comparator, or like the redstone level of this redstone, which is 0 to 15, obviously, so that's a hexadecimal number, and translates it to binary.
Yeah.
So the way this works,
how?
It is very complicated, but I'll try to explain it as best I can. So this one currently outputs 0.
Yep.
Which means that all of these comparators running out from this block also output 0.
Yeah.
The redstone would go through, but because there's no power, it's not going anywhere. The idea is that if that it goes in this direction, and then this one will compare if it is larger than, or I think it's if it's equal than or larger than this power from this comparator. And this comparator is outputting from this lectern. And now I'm going to quickly explain what the lectern does. So, come over here. So, as you can see, lectern, currently 0 input because there is no book. I will give you a copy of this book because it is a useful book. If I place the book, then it is on page 1 by default, meaning an output of 1. And then you can flick through the book, and as you do so, you change the signal strength.
Oh.
So
that's an interesting concept.
Exactly. So what I did is in this book, I just basically on each page, if you take a look, I just noted each number in the different number systems. So decimal is what we use as normal human beings. Then underneath hexadecimal, then binary, and then octal.
Why don't you have 16 pages?
Because it goes
because now it goes from 1 to 15.
Exactly. The thing is though, if you want that 16th bit, or like that 16th output,
yeah,
that's 0. You don't need the for that. There you go.
Well, yeah, but then how do you remove the book while the thing is functioning? Since
you don't need to. What you could do, let's say you want to be able to alternate between
1 and 0.
Sure, 1 and 0. What you could do is place a lever here. Because the input into the side is larger, it will not output.
Wouldn't it be way simpler to just add 1 page?
No.
To function as to 0?
No, because that's not how it works. Because the way this works, books are on page 1, there is no page 0. And you can't add a page 0.
I understand, but the strength of redstone goes up to 16.
No, it doesn't.
It doesn't?
No, look.
It's only 15? Oh. I was wrong.
So that's what the book does. Here's a copy of the book for future reference. And so what I've done here is, since this is the bit that means 4, right? Over here. The one I'm standing on. This one means 4. So this lectern is on page 4. So if you have 4 inputs, if this signal strength is 4, then it is allowed to propagate to here, turning on this redstone lamp. What happens then is that because this one is turned on, this torch over here is turned off. Depowering this redstone, depowering this repeater, allowing this comparator to propagate the signal, and this signal is the same. It's 4. So this way, you subtract the 4. Now that you've found the 4, essentially, you subtract it, and then you go down the line and repeat the whole process. So let's say you would have a 5th input, then this would result in a 1. And then it would continue. And then here, this lectern is on page 2, to subtract a 2, should that exist. In this case, it doesn't, because we've already subtracted 4 from 4, meaning we're on 0. So this one does not turn on. And then finally, this one also doesn't turn on. But if I unflick a lever, then it doesn't find the 4, it doesn't subtract it, so this one is 3. This redstone dust right here.
Yep.
Which then is allowed to pass because it's bigger than the 2 from this lectern. So it goes over here and is outputted, turning off this, allowing this to propagate, so it subtracts the 3, so then this redstone dust is 1. And because it is 1, and it's the last in the line, it then is propagated to the lamp. If I turn off another one, then as you can see, subtracting 2,
2 from 2
is 0, so this one doesn't turn on. And then finally, if I
subtract 2 from 1, it lasts to 1 pass.
Yeah. So if it isn't able to get the lamp, then it doesn't subtract the 2, meaning you just have the 1, and then that's it. And if there is no input, well, obviously nothing happens. It looks like a very complicated circuit, and it is difficult to explain, but that is what this thing is.
It's difficult to wrap my head around the different comparators here and fully visualize what it does, but I understand the gist of the contraption.
Yeah, exactly. So basically, it just runs from the largest bit, and you can expand this infinitely, of course. So we could make an 8-bit version of this, but it basically just goes from the largest bit down to the smallest bit, and if it finds a bit, then it subtracts that bit from the number and then continues with the remainder to then eventually be able to make it work. So that is what I've been up to in between episodes. Time to get into maths.
Oh no.
I'm going to start off by explaining the maths in Minecraft.
Okay.
And then we're going over to Turing Complete to implement the thing. Because the next thing we're doing is a half adder. And what that basically means is that it is a small circuit that is able to add 2 1-bit binary numbers together. So we're first going to go over how normal addition works. So let's say you have 14 plus 6, for example, right?
Yeah.
On this sign over here.
Oh.
Get over here. So 14 plus 6. So the normal method to do this, right, would be to add... No, not there. Is add the 6 and the 4.
Yeah.
Right? Like that. And then you need to carry a 1.
Yeah.
And then you see 1 plus 1. So that results in a 2.
Yep.
Which means the result is 20. That's how it works in decimal. In binary, it works in a similar way. Because we're working with a half adder, this means that we have 1 bit. So this can be either a 0 or a 1. So if you have 0 plus 0, that obviously results in 0. That makes sense.
Yep.
If you do 0 plus 1, then that results in 1.
Yep.
If you do 1 plus 0, then that obviously also results in 1. If you do 1 plus 1, then that would be 2. And 2 in binary is 2 bits. That is not possible. So therefore, you need to output a 0 and then carry the 1. And that is a separate output. So that would then go into the next half adder. So that means that our half adder also needs to be able to take in a potential carry. So that means that if you have 1 plus 1 plus 1, well, that would be 3. And 3 in binary is again 2 bits. So we need to output a 1 and carry the 1. So that's kind of how it works. I guess is the best way I can explain it. I'll quickly add the one that's supposed to be carried here. But that's basically how it works. And
I think at this part we will have a basic understanding of how binary works.
I hope so. And if not, then I'll try to explain in the
There are a
comments
lot
if
of-
someone has questions. But
Yeah,
but
there are
this
a
is-
lot of resources to find for that. And
But
we
this is
also
what
explained in
our-
the last episode.
yeah, this is what our circuit should do. So if there's no input, then it doesn't do anything. If there is one input, then output 1, and if both are on, then output 0. That sounds an awful lot like a XOR gate.
Yep.
And then if both inputs are on, or even if all 3 are on, then you need to also output the other, give the other output a 1, which is the carry. So with that explained, let's hop over to Turing Complete and build this thing. Right. So I explained a half adder and a full adder pretty poorly, so I'm going to go over it again. A half adder is only able to take in 2 inputs, which is the 2 1-bit numbers that you're trying to add. So that would be input A and input B. And as I pointed out in the video, the sum is indeed a XOR gate, and then the carry is activated by an AND gate. That's all a half adder does. So it only looks at the 4 basic possibilities. So 0 plus 0, 1 plus 0, 0 plus 1, and 1 plus 1, being 0 and then carry 1. That's all a half adder does. A full adder uses 2 half adders to allow a carry in, which is the C in right there. This circuit is a bit more complicated, and I'm going to explain how it works, but both inputs A and B run into the first half adder. The sum of that half adder runs as an input to the next half adder to be added with the carry in, and then if either of those have a carry out, then you have a carry out, and the sum of the second half adder is the sum that you end up with. So this is the truth table that you end up with. So for example, if everything is 0, then everything is 0, and as you can see, if everything is on, then you need to carry the 1, and you need to have a sum of 1. And in any other case, if there's 2, or even if there's only 1, then only one of them can be 1. The C out again is only 1 if there are 2 inputs on, and otherwise the sum is 1 except for there. So I'll give you some examples. So this is example number 1, where A is 0, B is 1, and C in is 1. So this is 1, this is 0, and this is 1. Let's focus on this half adder first. The sum of this would be 1, and the carry would be 0. Then half adder number 2 gets a 1 and a 1, so that would be sum 0 and carry 1, which means that there's a 1 running into the OR gate and a 0 running into the OR gate, meaning the carry is 1 and the sum is 0. So the result of this is 0, 1, or technically 1, 0. And if we check 0, 1, 1, 0, 1, that is correct. All right. We measure the universe with numbers, so your machine must learn to count. Easy. Treat the inputs as 0 or 1 depending on if they are off or on. Add them together in binary such that the result is either 0 or 1. As with normal addition, if the result cannot be described with 1 digit, set the carry to 1. That is what I just explained. So this is your normal output, and this is your carry.
Yep.
So I just already explained that you need to use a XOR gate for the sum. I see that this thing doesn't have a carry in. Interesting. And then if both are on, then you should have 0 and then 1. So then if both are on, so you need an AND gate.
Yep.
Then ooh, that's fancy. I like that. Then carry.
You have the exact same position and solution as I have.
Oh, nice. Perfect. Okay.
Yeah. That's half adder.
Let's go build it in Minecraft. So I'm just gonna put some space in between. slash schematic load Zor slash paste. There we go, Zor.
And
Cool, right?
then we just need an AND gate.
Yeah. So actually, I probably should not have pasted it there. So slash undo. We can do this again.
We can duplicate signals, yeah.
And then slash paste. Like that. Yep. And then I don't have the AND gate set up yet. Actually, we're going to do this. Actually, no. This is still this. Yeah, so that is the... maybe let's give us a bit more space.
Oh, okay.
So, like, extend this a bit more that way.
And this should be the current sum.
Yeah, that is a sum. I'm going to use a little trick, which I think you might not entirely enjoy, but that you're going to have to deal with it. Although, shall I just space them one block apart?
You could.
I feel like that's probably the neatest solution. I need the lamp.
Oh, does that work? Oh,
Yeah, that works.
and branch off to the side, I see.
Yep.
And then this is the current.
Yep. So, 0 plus 0 is obviously 0. Then, next up, if I do one of them, then the current sum is 1. Then if I do the other one, then same story. If I do both of them, there you go.
Then it carries one.
Perfect. That's
and
it.
now we need to create a full adder.
Yeah. I guess the full adder does have the carry-in. I'm not too sure, but we'll see. Back to Turing Complete.
The thing
All right.
I like about Turing Complete is it gives you the components after you understand the functionality
Yeah.
behind it. So later on, you just have an adder.
Okay, this is going to get really interesting.
Yes, and then we're gonna have to do assembly. I wonder how you want to do that in Minecraft. I think we're gonna have to work with command blocks then.
Maybe, but I don't know. We'll see. Full adder. In the previous level, we added 2 inputs. This time we add 3. There it is. That's the full adder. Okay.
Yep.
Once again, blah, 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 blah. If the result cannot be described with... yeah, okay. So that is what I was describing earlier. One of, like, let's say input 2. That's the carry in, and then this is the carry out. So, a full adder would obviously need the a XOR gate.
Yep.
For these 2 inputs. Except it probably needs...
It needs a forked XOR gate.
Sorry?
You just need 2 XOR gates behind each other.
Like this, right?
Yeah.
And then that.
Yeah.
That. That.
That's the first part.
Perfect. I am gonna move this because I don't know what.
You can shift it. Yeah.
There we go. Bit neater.
Like hover over the button you just clicked.
Shift and drag. Oh, okay. Cool.
Just like your desktop.
Yeah. Cool. All right. No, I wanted to make this a bit nicer, but I guess not. Okay. And then for the carry, we need a 3 and. Or sorry, no, not even. No. Because we need to carry whenever there is 2 or 3.
Yep.
So
I shall look upon while I...
Yep, you do that. In the meantime, I'm gonna try to figure out the carry. Technically, I could do this, right? Where I just create every combination.
Wait, what?
What?
Wait, how?
What do you mean?
Wait. I have so many questions. How does this work?
How does what work?
The first part was correct,
It was.
but I don't know how it was.
What?
I need to think about this. I need to contemplate. How does this function?
Okay, this is getting messy real quick, so I'm gonna...
Tristan, it's genius. Think about it. Think about why the first double XOR gate works.
So that is this, and that, and then this one there. Why would this work? Let's see. If both are on, then this is... Oh.
Yeah. So all three of them are on, then the XOR gate won't be on. First one.
Very nice. Okay, so here I just make every combination, I guess. So I can just do this, and then do that, and then 2 and 3. That is confusing. I probably should have used colors.
Yep.
Does this work? No. Yes.
I wish you could just send each other solutions. Like mine is already beautifully color coded.
It works. Okay. Nice. And now we have a full adder. Adds 3 bits and outputs the sum and carry. Beautiful. Okay, let's build it in Minecraft. This is probably not the best solution, mind you.
I think it's the intended solution at this part.
Probably, but not the simplest.
Oh, the top part is very simple. How would you want to simplify the bottom? Since
no
you
idea.
do need to check.
Yeah, I don't know. This seems complicated to build in Minecraft, and I feel like there's probably a better way. Either way, we're gonna go over to Minecraft. Okay, so let's also put signs on top so that we can see like what each thing would be, right? Or not on top. Let's put it in front. So this would be input 1, input 2, and then carry in. Let's just do that. Not that it really matters which one is the carry and which one is the inputs, but just for simplicity, I guess.
And dum.
There we go. So this would be the sum. This output right here. And now we need to AND everything. Oh, I hate this. I hate having to AND things and every possible combination. It's so annoying.
No fear, Tristan.
Okay, wait. Let's start with what do you wait, okay.
No.
What are you doing?
So the top one I'm gonna use to AND both of these together, and then the bottom one we can use to AND right middle and left middle, a little further apart.
True. Let's do that. So, redstone there, and then we would want to split it into 2 separate AND gates. And then, oh wait, we can just use a target block. Oh, target blocks are great.
A little unorthodox, but this works.
Okay, I need more distance, actually. There we go.
And then...
Oops.
I'm gonna start grouping the outputs. So this is gonna be the sum, yep. Current sum.
There we go. And then run this.
Then I'll leave this here.
And like that. Beautiful. And then this needs to all be ORed, correct?
Every 3 outputs from the AND gate needs to be ORed. Honestly, I kind of like the design of this one. This looks
There we go, that's an OR.
satisfying.
And then we just need to extend this to there.
Wait, should we not use the color of OR real quick there? That's nope, that's orange.
Sure. That's concrete.
Idiot. Yep. Not beautiful.
Cool, that should work.
We are speeding through this.
All right, input 1. So everything's off. Then if I turn one of them on, oh.
Yep. No, wait, what's going on here?
Interesting. This makes sense.
Why is the
and
top
then...
end on?
Sorry? Oh. Yep. Which then currently isn't very nice. Then I need this.
Wait, but then if both of them are off, this one will be on, no? That's kind of an issue I ran into. Yeah.
Sorry. What?
Look, it's on.
Oh. What? Oh, it's because it's the inverted signal. Right.
Yeah.
Okay. So then that...
So that's why I had a comparator there.
Repeater.
Repeater, yeah. So we do that.
Then this was correct.
Oh.
Like this.
That's actually always surprising. But then why, if one of them is on, does this go on?
Because now this is off and then this is on.
But this should be an AND, not an OR.
Yeah, currently this acts like an OR.
What has I done wrong?
What if I do this?
The
that.
problem... No, since you invert, again, you don't want to invert. The problem is that it acts on reliably.
Sorry?
You shouldn't have to invert it. We just need to figure out why this is on currently and how to fix that.
So this is on, so then this off, on, off.
Yeah, that's fine.
That turns that on. Because if this is a normal AND gate.
Yeah. Wait, no. What? Now it's functioning. No?
Isn't it?
Wait. No. Nope. Now it's on. It's not functioning. Why is it not functioning? What's going on here? What if we don't use the target
wait,
blocks?
I have a better idea.
What if we don't use the target blocks?
There we go, I fixed it.
What did you do?
It's now a normal AND gate.
It appears to be a normal AND gate.
I fixed it.
How was that the solution?
Because you had a torch here, and I replaced the torch with redstone, thereby
so
getting the original input again. And I guess just the extra inversions, first of all, are not necessary, and secondly, just cause more chaos.
Yeah. Well, simplify. Let's go.
Go. That's it.
Does that mean we can place it one lower?
No, I don't think so.
I think so. You know?
Oh wait, actually. Maybe. I hate that you do this. Okay, like this. And we don't even need this now. Ooh, this is very clean. Look at that.
Beautiful.
Yep.
The more you can simplify.
And then I just need to run this to there. Cool. So now this works, because if you now then add a second one, then you carry one and you output 0, and then if all 3 are on, then everything is on. Beautiful. Okay, that's a full adder. Awesome. All right, back to Turing Complete.
Designs are getting simpler and faster as well.
Yep. I'm sure there's probably a way to do this better, but we'll see before next episode. Yeah. Right, back to Turing Complete. So the full adder is completed, so now we keep going. Oh, we don't keep going. We need to... We can't add bytes yet, and we can't do a bit switch. We need to double the number. Alright, double the number. The input and output of this level are using bytes instead of bits. One of the 2 new components you are given takes a byte and splits it into bits, and the other does the opposite. Using those components, figure out how to double the input. Oh!
Okay, so this is not exactly difficult.
No, this is very easy. This is bit shifting.
Yep.
And bit shifting works because if you make every... if you take every bit and you move it if you shift it 1 to the right, I think that's a right bit shift, then as you can see, the 1 becomes the 2 becomes the 4 becomes the 8 becomes the 16 becomes the 32 becomes the 64 becomes the 128.
Yep.
And then the 128 can't be connected to anything because it's too big. And that effectively doubles your number.
That indeed is that. So how do you want to do this in Minecraft?
Oh god. Fantastic question. Okay, I think we should have because we can't obviously have binary number like full numbers that then have to be translated into binary, right?
Yeah,
but we can bit shift.
Actually, we could represent it. No, not yet.
So I quickly want to check, like, what if I...
How do we work with binary in Minecraft here?
What? How does this... What? Stop. Is this just taking random numbers? It is. Okay, wait. What if I turn everything... Like, what does this entail? Oh, wait. There.
Yeah.
So that's 0.
Yeah.
And that is like it's intended.
0 is the carryover. Yeah.
This doesn't do anything.
That's the carryover right now, since you can't effectively double that.
Okay.
You don't have to
well, this should be pretty simple. So let's go over to Minecraft.
So we need one input with the possibility of 8 different strengths.
8?
8.
How so?
We don't use the 8th, but we do need it.
Why?
1 to 128. 1, 2, 4, 8, 6, 32, 64. So we really want to...
Alternatively, and probably easier, is to just...
back.
Hello there. I've currently put 2 lecterns down. I don't know if they're super useful, but currently, because each lectern is 4 bits at most, because it goes up to 15. I think what we need to do is to build the binary decoding machine twice. one for each lectern, and then run the output of that so that we can translate it to binary, right? And then run the output of that thing into the bigger lamps, if that makes... They're like the double lamps, if that makes sense.
Oh lord, Tristan.
What?
I'm looking for designs for like an 8-bit adder.
Yeah.
In Minecraft, and it leads to monstrosities like I've not seen before in Minecraft. All right.
Oh my god. That is terrible.
This is basically what we are going to, but
yeah,
if we want to make an actual computer later on, we would need to have a whole bunch of these, I think, no?
Presumably, yes.
Oh wait, I found a compact design. Well, this is okay. This is actually pretty cool.
What?
Using observers and tractors as inputs. Wait, this is actually kind of cool. Okay, so he's using pistons underneath observers, but why is he using so much tracks?
I don't know.
Is he using tracks as like a supplement for Redstone?
Maybe.
I think he is.
That would make sense, given that you can run that like
Wait, this is
next to
actually
each other.
quite a smart thing. Wait, the man actually made a calculator that also remembers things, and it's only that size.
What on earth?
Oh Jesus! What have you done in the meanwhile, Tristan?
This is the signal strength to binary translator.
Oh lord! But now we just need to double the output.
Kind of. This is for half of the number. So this thing will deal with the smallest bits of the number.
Mm-hmm.
So we're almost done. So this would be all the outputs. Like so. So since this is the maximum thing, I'll quickly place lamps just so you can see that this works. Wait. Did I mess up? Oh, I did mess up. This is wrong. There we go. Alright, that should be fixed now. Okay, so take two. So 4 bits on. As I scroll back, it doesn't work. What? Why? $14. Page 8, page 4, page 2. Oh, I'm an idiot. I forgot that this had to be a target block.
Nice.
There we go. Take 3. That's 13.
Yep.
12.
Yep.
11.
Yep.
10.
Yep.
9.
Yep.
8.
Yep.
7.
Yep.
6.
Yep.
5.
Yep.
4. 3.
Yep.
2. 1.
And 1.
Okay. So this controls the bottom 4 bits. And now we build this entire thing again.
For the top 4 bits, and then we have
Exactly.
to double the number.
So,
But doubling the number is not really something we need to do.
what do you mean?
Well, as in, like, it doesn't really matter right now. Well, since we don't have anything to output it in to double it.
I mean, no, but we still can.
What would your suggestion be?
First, let me just real quick. There we go. So now we can run this into a block. The redstone. So this one, right? This is 1. So this output bit, we run into the second bit, which would be here. And then, okay, let's start with the biggest one. This one we don't run anywhere, right? Because that's the biggest one. We can't double that. The next one, we can run up and over. Actually, what am I doing? What are you doing?
Duplicating?
No, we
Oh,
don't
no,
need that.
yeah, my bad. You're right.
Okay, so that is that one. Then this one goes into the into the lamp below that. And again, I think it is... Oh, it's not inverted. Perfect. Okay, and I'm going to assume that we are going to need a repeater there. Then finally, this one. Beautiful.
And then the bottom one.
The bottom one doesn't have an input, does it? There's no number that you can double to get 1.
True.
Okay, so this works now. So if we make everything 0...
Doubled numbers.
This thing is a bit of a monstrosity, but we can't really get around that very easily. So now it's 0. And then if I turn it... Oh, actually we need independent 0 signals.
Do we?
Yes. Because we want to be able to turn this one off.
Yeah. Yep. I'm kind of proud of this.
Yeah, fair.
Looks cool.
Agreed. Okay, so now I can make it 1. Which then becomes 2, because it's doubled. And
If
then
you look at this from top down, it looks pretty cool.
Oh, that is cool.
Yeah,
Okay.
look at it from my angle.
Where are you? I've lost... Oh, there. That is sick. All right.
Why is this so satisfying?
All right, so check the output. So 1 doubled is 2.
Yep.
2 doubled is 4.
Yep.
Then 3 doubled is 6.
Yep.
4 doubled is 8.
Yep.
5 doubled is 10.
Yep.
6 doubled is 12. There we go. So now we're on 32, which is the double of 16, which is the first
Wait, do we have
thing here.
31 already?
Sorry?
Do we have 31 already?
How do you get 31 from doubling?
The timing on that. You're right. My bad.
Stupid. Okay, so then, I mean, you can flip through that one, but if you then unflick and then go back to page 1 on that one, then we can continue looking at how this works. And I think then maybe we leave it there for this episode.
Page 1.
Yep. So that would be 34. The only unfortunate thing is that because redstone dust is limited, you maxed the counter.
Yeah.
Because it's limited, we need to use 2 inputs with lecterns. Because that's all we can encode in one singular redstone dust. One dust can be at most 4 bits. And we can't have a singular line being, you know, all those bits. All the 8 bits. And technically we have 2 extra inputs to make a 0 input. But whatever. Alright.
Is there a mod that could double the amount of bits we allow in Redstone? Or are we gonna do this modless?
Sorry?
Or are we just gonna do this pure modless?
Unless we can think of a better solution, or there is a mod. I don't know. If there is a mod, then we might end up using that. If there is no better solution, then we need to think of a better solution if we can. And
We could just make the mod ourselves and recode Minecraft fundamentally.
Anyway, thanks everyone for watching, and we'll see you next time. Bye.
Yeah, bye-bye.